In this lesson we will talk about motor protection. As we know that motors are being used in industries nowadays. In fact, motors are the backbone of all the machinery that are in the industry as of today. So it is important that we provide some form of protection for the motors. So over here I have the motor curve, which is the TCC curve. Over here, as you can see from the curve, at the initial condition, that is at 100% of slip, the current drawn by the motor is likely 600%, then its full load current. So at a particular instant this current reduces, and when the slip becomes like say to 3 to about 5% of slip, you can see that the full load current appears across the motor. So motors are somewhat different from that of your existing loads, lump loads, due to these characteristics. So when providing protection for induction motors, you have to consider this curve and assign your instantaneous overcurrent protections beyond this point over here. So let us go a little more further. In case of motors, we also need the thermal overload protection. So let us see what the thermal overload protection is. The thermal overload protection or overheating of the motor could lead to insulation failure and thereby damage of the winding. So it is recommended to have a proper motor thermal overload protection. The motor should be protected against the following conditions. So here we have the following conditions of the motor, that is the mechanical overloading and stalling of the motor shaft, low supply voltage, single phasing of supply mains, unbalancing of supply mains, sudden loss and rebuilding of supply voltage. So the main aim in case of motor protection is to provide the overload protection, and the thermal overload protection is provided by using a relay or any other mechanism such that the curve of the device will be in this region shown over here. So that is the main essence of the thermal overload protection. When the motor becomes overloaded, the motor could actually sustain certain amount of overloading, and if that amount of overloading exceeds the threshold value, you actually need to stop the motor from overloading or protect the motor from further overloading and prevent the thermal breakdown of the motor. So let us go to ETAP and see how we can implement motor protection. Here we are in ETAP, and as you can see, I have already made some of the protection schemes for the motors over here. I have made 4 different protection schemes, as you can see over here, whereas this protection scheme and this is the same, and so these are the 4 different protection schemes that I have implemented for motor protection. So all these motors are identical motors, which are 50 kilowatt motors, and over here you can see the different protection schemes. For the first protection scheme, I have used a motor relay. For the second, I have used an overload protection relay with a circuit breaker, and over here I have used a fuse, whereas in this case I have used a solid state trip relay. So let us go about explaining each of these protections over here. So first thing we have to look at is to get the starting curves for the motor, and in order to get the starting curves of the motor, you will have to double click on the motor, go to the protection tab over here, and you can see we have the starting curve with a constant terminal voltage, and you can also obtain the starting curve from the acceleration study, which is the dynamic acceleration study. You can conduct a dynamic acceleration study and use the value of the starting curve from the acceleration study, or you can use by simply providing these values over here. So when I check these boxes over here, I get the starting curve for different voltages over here, for 100% of voltage, 80% of voltage, and 110% of voltage. So you can plot different starting curves in the same graph itself. So the acceleration time will be provided by the manufacturer in the data sheet. For in this case I am going to provide it the acceleration time of 1 second. So I have checked in the smooth corners over here, and I have also included starting devices on overload heating devices and equipment cable along with the starting curve over here. And you can see the asymmetric lock rotor current. I have given a asymmetric factor of 1.6. If the manufacturer provides in this data, you could select any values from about 1 to 2. The asymmetrical factor determines how much the locked rotor amperes will be from the symmetrical point over here. And next thing what we have here is the thermal limit curve. The thermal limit curve is actually the damage curve or the thermal damage curve of the motor. So we have 3 options over here. Hot start. So the hot start is usually used to refer to a motor that has been running for some time, so that the motor temperature is already at the rated temperature. And whereas in the cold start we have the motor at the ambient temperature, and during its operation it reaches its rated temperature. So a motor which is already at the rated temperature will have lower thermal limits, whereas a motor that is just been started will have higher thermal limits. So that is the difference between the hot start and the cold start. These two are the thermal limits of the motor over here. So I can provide in the stall time. The stall time or the hot to cold ratio will be provided by your manufacturer. So this will be like 7 and 10. For my case I am going to tick in the hot start and the cold start. Actually it is just enough to use the hot start itself, because you do not want your protection devices to be covering beyond the hot start point. For in this case I will use all these values and the stator curve points. When I click on the points you get the stator curve, and as a multiples of the full load amps or as in amps itself, I can add in additional values or insert or edit any of these values. This is also provided by the manufacturer itself. So those are the values that you will have to use in this case of motor protection. So let me close this. And next thing which we will also have to consider is the cable protection. So when I go to the motor I can use the cable. So this option gives a cable to be provided right before the motor, but I have directly connected to this bus. In your case, if you are connecting the motor to the bus by some means of a cable, then you will have to provide in the cable ampacities and the cable voltage drop in the machine itself. But for this example I have used a cable that is connected between bus 1 and bus 2. So in this case we will have to provide in the ampacity values and the protection in the cable editor itself. So I will have to change the cable in this case, because I will have to use the above ground trace according to the ICA standards. So using this cable size will not calculate the ampacity. So let me go ahead and change the cable. I am using XLPE cables, so let me choose this cable itself. So the rated voltage will be 1 kV itself is enough, because our voltage is 0.415 kV. I am using this size because our ampacity calculation requires us to have at least a size of 1 bar O AWG. So I have the rated ampacity over here, so that's fine. And in the protection tab, this page is for the cable damage curve. So in order to obtain the short circuit currents, you will have to go to the star mode over here and fault this bus over here, and I'm going to run or update the short circuit KA, and let me do that. So now when we go to the cable over here, you get to go to the protection page, and you can see that the short circuit values are updated over here. So that's it, and once that is being done, then next thing which we will have to do is go to the star view. So I am selecting the motor and the cable, and let us create a star view for the same. So here we are. So our cable damage curve is way beyond our motor starting curve, which is good, and you can see the motor starting curve over here. This is the asymmetric locked rotor current. So let us measure how much our asymmetrical rotor current is. So this is about 890 amps, and the full load current is 91.7 amps. So as explained before, this is somewhere around roughly 600% of the full load amps. And here you can see we have the thermal limit curves over here. So these are the damage curves for the motor. The hot portion is over here and the cold portion is over here. Now let us enter into the protection scheme. So let me select the relay over here. So the relay which I have used is ABB REF 542 plus, and you can see the CT ratios. The output, I have configured it to open this contactor over here, and you can have both these elements over here. So here we have the 50 element, it's an instantaneous element. So we have both 50 element and the 51 element. 51 element is the overcurrent IDMT element, and we have the ground fault, etc. Beyond that we have the overload protection as well. So we have the thermal overload protection and the acceleration, the jam. The values for this will be set using the star mode. So we will set these values in the TCC. So we will see how we go about doing that. Now we will select the entire branch over here, including the relay with the cable and the motor. And when I go to create the star view, you can see this over here. So removing the contactor, and the cable damage curve is way beyond the motor starting curve, so I will remove the cable as well. So here we have the motor protection elements over here. This is the 51p element, so this is the overcurrent element, and I'm going to adjust this somewhere around here. So that's been done. Now you can see that this portion over here, which is the overload element, is way beyond the cold thermal curve. So I will have to bring that just about here. That will be before the hot damage curve. So that being done, then over here you can see the acceleration portion. I will have to adjust the acceleration portion over here, so that when we have a locked rotor condition, then the relay will pick up and operate the contactor over here. So start protection curve is also available, and over here we have the jam protection. So when we have a condition when the rotor is being in the jammed position, we need the relay to operate. So I am going to provide it as close to the starting curve over here, because beyond this portion you will have the stalling condition over here. So this is how I have configured my protection. So let us go back to the star mode, and I am going to insert a fault at this bus. So let us see. Okay, now this protection worked well. So the next protection scheme we will be discussing is this over here, which involves a breaker and an overload relay. So the overload relay is available over here in the toolbar as inline overload relay, and the device number is 49, whereas the motor protection relay is available in the instrument toolbar as the motor relay. So let us go to the star mode in order to analyze the curves for this protection scheme over here. So I am going to create a TCC, and in this case, as the motor damage curve is way beyond, I am going to delete this over here, and I have already set this protection scheme over here. As you can see, the combination of these two curves provides both the overcurrent protection as well as the overload protection. So let me show you which overload relay I have used. This is the Siemens 3UF7, and you can see the thermal element is there, and this type is a class 5 3-pole, and I have set the trip range which is based on the TCC graph. So I have turned off both the jam element as well as the ground element. If we want, you can use these two elements as well. So that being said, and the circuit breaker which I have used over here is an ABB 3-pole, and you can see the long time, short time and instantaneous pickup curves over here. So let me insert a fault, and you can see the circuit breaker operation over here. And the next protection scheme which I have used is the fuse over here, and this type of motor protection is used for very small motors and is not recommended for very large motors. For large motors, you actually need a motor relay or a overload protection in order to provide motor with sufficient protection, whereas in the case of fuse, you do not have the flexibility of varying the TCC curve of the fuse. So let us go about seeing the curves in the TCC view for the fuse, and as you can see, let me show you that the fuse rating is way beyond the thermal damage curve of the motor. So I will have to adjust this before the cold thermal curve. So this is the protection over here. So this type of protection is used for very small motors. Let me select the size. So this type of protection is used for very small motors and is not recommended for high power motors. So this is one type of protection over here. So the next protection scheme that I have used is by using a solid state trip relay. So the solid state trip relay is available in the instrument toolbar as MV solid state trip relay. So let me go to the library of the solid state relay, and at present we have only a single manufacturer, which is the Westinghouse, and we have two models, that is the Digitrip 3000 and the Digitrip MV. So let us go to the TCC curve to see the curves of this portion over here. So here you can see we can adjust these portions accordingly. So this is the flexibility of using a solid state relay over here. You can actually adjust the short time, the long time and the instantaneous periods over here. So this is other method of providing motor protection by using solid state trip relays. And over here I already have this other branch for this type of protection over here. I want to show you that you can use the curve from a study as well in order to plot the curves. So I am going to turn off this starting curve, and I have the hot and cold, all the other thermal limit curves available. So let me go to the TCC portion of this graph. So here we are. So in this case we will have to adjust the overload element, or we actually do not need this overload relay. The protection provided by the circuit breaker is enough in order to provide the protection in this case. So this is how you provide motor protection in ETAP, and I will make this file available for download, and see you in the next lesson.